Korea. This slide shows today's presentation contents. First topic I'm going to present is necessity of combining fan design method, optimization algorithm, and the CFD analysis method. Next, I'm going to explain fan design and the performance analysis method, so-called the FANDAS code, which is used in this study, and its verification. And then I'm going to talk about how to combine the FANDAS code with optimal design and the CFD analysis method for developing a variable pitch axial flow fan. Finally, let me make a conclusion of this study. As an introduction, I'm going to explain the role and the importance of the design and the performance prediction method in fan development procedure. As you can see in the general fan design procedure of this flowchart, once fan design requirements of flow capacity, pressure rise, efficiency, and even noise level are given, we can determine main design parameters such as the tip and curb diameters. And we can make a blade angle distribution and the camber lines of a blade section. Next design job is to make airfoil thickness profiles of the section and to stack the section elements along blade span height. Based on the 3D fan blade geometry, we can make a check the fan performance by performance prediction method. We developed the FANDAS code, which combines the design and the performance prediction method, and can be used as a design tool of fan development process. Next, CFD method can be also used to verify the flow and the performance characteristics and to make a design revision of the fan. Recently, an optimization algorithm has been combined with the design or the CFD code to optimize fan design. Final fan design model is manufactured and tested in fan performance tester. So, in this study, we're going to explain about the FANDAS code and how the FANDAS code is combined with the optimization algorithm and the CFD simulation method. We will also talk about the application example of a variable pitch axial flow fan. As an introduction, I'm going to explain the role and the importance of the design and the performance prediction method in fan development procedure. As you can see in the general fan design procedure of this flowchart, once fan design requirements of flow capacity, pressure rise, efficiency, and even noise level are given, we can determine main design parameters such as tip and herb diameters, and we can make a blade angle distribution and camber lines of the blade sections. Next design job is to make airfoil thickness profiles of the sections and to stack the section elements along blade span height. Based on the three-dimensional fan blade geometry, we can make the check the fan performance by performance prediction method. So we developed the FANDAS code, which combines the design and the performance prediction method and can be used as a design tool of fan development process. Next, CFD method can be also used to verify the flow and the performance characteristics and to make a design revision of the fan. Recently, an optimization algorithm has been combined with the design of the CFD code to optimize fan design. Final fan design model is manufactured and tested in fan performance tester. So in this study, we're going to explain about the fan dust code and how the fan dust code is combined with the optimization algorithm and the CFD simulation method. We will also talk about the application examples of a variable pitch axial flow fan. This slide shows the calculation processes of the fan dust code from design step to performance prediction step. We can determine design parameters for three-dimensional fan blade geometry, such as tip, herb diameters, and the chord length, and then make a 3D blading design from blade angle and the profile distribution, which are very important parameters for fan performance improvement. Using through flow analysis method of a quasi-3D flow scheme, we can analyze the spanwise distribution of total pressure, flow velocity, flow angle, and so on. Finally, the fan dust code calculates the fan performance characteristics using mass averaging of the through flow analysis results, such as the flow capacity versus pressure and flow capacity versus efficiency. In this slide, I'm going to introduce three blading design methods of the fan dust code. We have three design methods to determine the tangential velocity or the outlet angle alpha 2 of blade section. Free vortex FVD, combined vortex CVD, and the controlled blading design CBD method. As you can see in this table, FVD and CVD calculates the outlet angle distribution by this simple rule of the function of the radius. But CVD can give more flexible outlet angle distribution for more improved performance than the FVD and the CVD. Using this design method, we can calculate the stagger, the camber, and the setting angle from blade inlet and the outlet angles, and these camber sections are stacked to form two three-dimensional blades. Especially variable pitch fan operation gives the change of the stagger angle and then results in the change of the incidence angle and the flow capacity range of the fan. So the blade angle distribution design is very important for high performance and the wide flow range of the fan. And for this reason, we selected the CBD method for variable pitch fan design. This slide shows application examples of the fan dust code. Three automotive cooling fans are designed by FVD, CVD, and CBD methods to construct a different blading design, as shown in light figures. We made a CFD model to verify the Fandas code predictions. We used the fully 3D and steady-state flow length calculation method with the frozen rotor scale, and generated a mesh system of a chamber-type flow domain with about 1 million elements. We used the K-omega SS tablets model. You can see streamline and pressure distribution of fan blades, which are analyzed by the CFD method. You can see three Stagger and Camber angle distribution designed by FVD, CVD, and CVD method. The Camber angle of the CVD is higher than the FVD and the CVD. The stagger angle in tip region of the CVD is somewhat lower than the FVD and the CVD. It can be seen in light figure. The Fandas predictions will agree with the CFD and test results. The performance and the efficiency of the CVD fan is more improved than the FVD and the CVD fans. Another example of the Fandas code application is the general application fan, which is used in air conditioning system. You can see the design requirements and the main design parameters. Design flow capacity is 270 cmm. Design pressure is 250 Pascal. Tip diameter is 63 centimeters. Chord length change from 87 to 71 millimeters. And the RPM is 1440. In light figures, you can see the stagger and the camber angle distribution of the fan and the 3D fan geometry. We can compare the Fandas prediction and the test result of the fan and the variable pitch operation condition, a pitch angle of 25, 35, and 45 degree. You can see good comparison results, which show that Fandas code is very suitable to predict the performance of the variable pitch. This slide shows the structure and the strategy of optimization study of axial flow fan. The Fandas code I mentioned before is used as a simulation engine of design optimization study. We use the CVD as a blading design method. We have a total 13 design variables such as chord length, camber, and stagger angles, and 16 design constraints are used. The optimization algorithm we use is hybrid meta-heuristic algorithm HMA, which is a function-based method. After iterative computation of design variables, we check the convergence histories and the violations of design variables and the design constraint, and then obtain the final optimal solution of the axial flow fan. You can see the design variables of the optimization problem: 5 camber angles, 5 stagger angles, and 3 chord lengths, which are defined in this table. You can also see the design constraints for flow capacity, pressure, power, blade angles, and the blade solidities. From right convergence history curves, you can check the design variables, the objective function, and the design constraints are robustly converged to optimal values with no violation. Final optimal design solutions are obtained as shown in this table. The optimal fan efficiency is 82.4%, which is higher than the initial design of 80%. You can see the three-dimensional fan blade geometry obtained from this optimization study. We also apply the CFD technique to optimal fan model. We use the schematic sampling codes for CFD modeling and the simulation. You can see the 3D massing in flow domain inside circular duct with about 3.3 million elements. We use the MLF scheme for interface between rotor and the stator blades. And we also use the Lance equation solver with the K epsilon turbulence model. You can see the pressure lines of air passing through the rotor stator blades like this. In this slide, you can see good agreement between the Candace prediction and the CFD calculation results. In these figures, you can see the total pressure exceeds the design requirements of 55 millimeter H2 at 3,300 cubic meter per minute. And as the pitch angle of the fan blade changes from negative angle to positive angle, the fan flow range widens and the pressure curve gradient increases according to the flow rate. And power is capped lower than the design requirements of 55 kilowatt, and the power tends to increase as the rotor blade pitch angle is increasing. The predicted efficiency are 82.78% by CFD and 86.50% by FANDAS, which are higher than the design requirement of 80% and maintains a relatively high efficiency of 80% or more in a wide flow range through changes in the fan blade pitch angle. The manufacture and assembly of the prototype of optimal fan model in progress, and then the optimal fan design is verified through testing and confirmed as the final model of commercialization. Finally, let me make conclusions. For high efficiency and wide flow capacity range fan development, it is necessary to develop and apply a computerized development system which can combine design method, performance prediction method, and CFD analysis method with design optimization algorithm. The second conclusion is the Pandas code is used as a fan design tool, which is capable of performance prediction and has been verified by test and the CFD result. And then Pandas code can be used for high efficiency fan development. Design optimization study of a variable pitch fan by combining the Pandas code and the optimization algorithm is successfully conducted. And optimization results are verified by CFD simulations and also show more remarkable efficiency improvement and the flow capacity expansion compared with the existing model. Thank you for your attention.